Right, so good morning, everybody. We've finally got to part of the course I've been anticipating for a long time, which is about Gödel's incompleteness theorems. We already did Gödel's completeness theorem for our proof system in an earlier lecture. The completeness theorem we managed to cover in one lecture. The incompleteness theorems are quite a bit more substantial, and it's going to take us 4 lectures to cover them. But they are, in my view, the most interesting part of the course, so it's worth spending time on them. So I think this is lecture 10, and in that case, it's going to be lectures. Let's find a better quality back pen. Lectures 10 to 13 are going to be Gödel's incompleteness theorems. And as I say, it's going to take us 4 lectures. So today's the first lecture. So this is I think today's the 18th of April. So then we've got second one on the 25th of April. Then, as everyone who is Slovene will know, but there are some non-Slovenes here, the 1st and 2nd of May are holidays in Slovenia. So there's a holiday week on the 2nd of May. So the third lecture is the 9th of May. And the last lecture on Gödel's incompleteness theorems is the 16th of May. So it's going to take us a lot of time, but we're going to get to one of the main punchlines already next week. So next week, we're going to have the theorem that any consistent, computably axiomatizable, let me just say axiomatized, theory of arithmetic is incomplete. So consistent means it's consistent, as you know. Computably axiomatized we did last week. So we have a set of axioms that's computable. We can test whether a sentence belongs to our set of axioms or not. Theory of arithmetic means it's a theory that's axiomatizing truths about the natural numbers. So we're trying to axiomatize truths about the natural numbers, and if we have a computable axiomatization, unfortunately, our axiomatization is incomplete. So you will remember from right at the start of the course, an incomplete theory is one in which there is some sentence for which neither that sentence nor its negation belongs to the theory, or is provable in the theory, if you like. So if we have an incomplete theory about the natural numbers, well, that sentence that neither it nor its negation belong to the theory, either that sentence itself or its negation will be true. So either way round, whichever one's true, we have some true sentence about the natural numbers, which is unprovable. So if we manage to get that already next week, well, why go further? Well, in a sense, next week's result's not going to be very satisfactory in a couple of ways. First, it's going to rely very heavily on computability theory, which I'm not going to go over the background computability theory in this course, but essentially it's going to be a bit of a borrowed result. But also then the true but unprovable sentence is not very interesting. So the week after that, we're going to follow Gödel's own approach. When, in fact, in the next 2 weeks, we're going to follow Gödel's own approach. This is a more modern approach next week. So Gödel's own approach finds interesting examples of true but unprovable sentences. So the first approach is what's called Gödel's first incompleteness theorem. And in that, Gödel uses some clever trickery to construct a sentence in the logical language we're going to have for arithmetic, where one way of reading the sentence is the sentence, so this is a formal logical sentence, but the sentence says, I am unprovable. So here, I doesn't mean me, it means the sentence. So the sentence says of itself, so it's what's called a self-referential sentence. This is going to be some property of numbers, and it's really unclear at this stage until you sort of see the details how you can have a property of numbers that is able to refer to itself, that you can interpret that property of numbers as saying, well, I am a sentence talking about numbers, but I'm actually talking about my own provability in doing so. There's something quite clever there, but that sentence, I put it in quotes because that's paraphrasing it, it's really a property of numbers. That sentence is itself is true, but unprovable. So this is it's a very clever sentence, how one constructs it, but it's rather contrived. So contrived means sort of put together for a very specific and rather strange purpose. So Gödel's second incompleteness theorem is what we're going to do in the last week on Gödel's results. That has a more natural sentence. This says, the sentence that says that the theory of arithmetic we're working in is a sentence that says that that theory is consistent. So again, I put it in quotes because again, this is a property of numbers, but we can state a property of numbers saying that the theory is consistent is unprovable. Or maybe let's put this in another way that it's usually paraphrased. So, where are the brothers? Yeah. Raisers, yeah. Good morning. Good morning. So maybe a better way of stating it is no consistent theory of arithmetic proves its own consistency. So if it's consistent, there's going to be a statement about numbers that says the theory is consistent. If the theory is consistent, that sentence is true. And then once again, that's a true sentence that's unprovable. I can't really go into more details at this stage because it requires all the preparation of the lectures in between to get there. Okay, so that's what's to come. What about today? Well, today we're going to set the scene for this by looking at the formal language within which we can express arithmetic. That's properties of the natural numbers. So today is simply going to be language of arithmetic. In it, we're going to get one very nice result, also due to Gödel, something I already mentioned, I think, in the first or second lecture of the course. I set you as a challenge. I'm saying more about that in a moment when we come to it. So the language of arithmetic. So we've considered lots of signatures in this lecture. With theories expressing properties of all sorts of mathematical structures. Kind of strange in logic that theories about the real numbers and about the complex numbers. So the theory of real closed fields, the theory of algebraically closed fields of characteristic zero, they're all they turn out to be decidable. I've mentioned these results a couple of times, so slightly beyond the material in this course. You might feel from your own experience with mathematics, I mean, real numbers, complex numbers, continuous things, very sort of, whereas natural numbers are somehow, well, they're discrete things. You might imagine the world of natural numbers is simpler, but from a logical perspective, it isn't. So discrete mathematics and combinatorial properties have actually turned out to be really hard from a logical point of view. We're going to be looking at the language of arithmetic, which allows us to formulate properties, formulate properties of discrete mathematics, and then we're going to get these surprising results that we don't just have a theory that's not decidable, but we can't even axiomatize the truths of that theory. So we're interested in the structure . So fundamentally, we're interested in the structure of the natural numbers with the associated operations on it. We're interested in the natural numbers plus suitable operations. Then we're going to choose the signature for including the operations. So we could take the signature we've been working with very often, which is the signature of a ring. Well, ring is not appropriate for the natural numbers because there's no negation, but semi-ring. We could take the signature. So we have 0 and plus, the one we've been working with very often, 1 and times. But for the natural numbers, it's traditional to take a different signature, which is equivalent to this. So following tradition, we instead, so we're going to have 0 plus and times, but instead of the constant 1, we have a unary function, the successor function. So here we have, use green. So it's constant, arity 2, and arity 1. The successor function is the function that adds 1 to a number. So this is very straightforward, but anyway, let me just. That's the wrong thing. So we'll call this signature this signature is what's called the language of arithmetic. L sub A, the language of arithmetic. So the idea is that S of x represents the function, represents x plus 1. So this is just a function symbol, so it's a way of building terms, the way of the term that adds a natural number. So we can, so the two signatures are equivalent, very easily the two signatures are equivalent because this already defines S of x in the first signature and S of 0 defines 1 in the second signature. So it's a triviality. We can represent the successor function in the first signature, the blue one, like that, and we can represent 1 in the second signature, like this. And from a mathematical perspective, the first signature is kind of more natural because it's the signature, as I say, that one uses for semi-rings or rings or something. So, but I mean, it might seem like that from a general perspective, it seems more natural. Actually, if you're thinking about the natural numbers, this signature is not unnatural because the natural numbers are generated from 0 by applying the successor function. So in a sense, this signature having 0 and successor is very natural for the natural numbers because 0 and S is kind of the algebraic structure that allows us to generate the natural numbers, and then we're identifying a couple of important operations on the natural numbers, namely addition and multiplication. So let me just write sort of benefits. They're not really strong benefits, but reasons for using LA. Sort of one is having what I've just said, so having S is natural because it generates the natural numbers. So S applied to 0 generates the natural numbers. Secondly, turns out when we come to axiomatizations next week, the axiomatizations are very naturally expressed in terms of the successor. The axiomatizations, these are next week, are given naturally in terms of the successor. And the third one is, if you read any literature on Gödel's theorem, sort of as additional reading, it's almost inevitably going to work with this signature. So it's consistent with Gödel's theorem in the literature. Okay, so we're going to use this language with the signature L sub A, so 0 plus times and successor. And first thing we're going to do is spend a bit of time looking at how we can express other operations and properties in this language. And let me just tell you where we're heading for the main result today. So one way of looking at this is we've got 0 and successor, those generate the natural numbers. Then together with the natural numbers, we're adding some operations. If we add addition, so addition is basically the repeated successors. You repeat the x plus y is repeat the successor on x, y times. If you add addition, actually you get a theory that's still a very manageable and decidable theory, but you can't express very much if you only have addition. So addition is, for x plus y, as I've said, is repeat the successor y. So it's repeat the successor on x, y times. Multiplication is, so x times y is repeat the operation of adding x to itself, y times. Oh, so sorry, repeat the operation of adding x to a number, y times. That's multiplication. So there's a natural next step of repeating an operation that number of times, which would be the operation which is repeat the operation of multiplying by x, y times, which would be the exponential operation. So we could also add the exponentiation to this theory, x to the power of y. Why don't we add exponentiation? Well, this is something I mentioned already in, I think, the second lecture. So a main goal today we don't need to add exponentiation to this signature because it's definable. It's definable in signature L sub A. I think I mentioned in lecture 2 that proving this was one of the Gödel's theorems. We go to Gödel's first and second incompleteness theorems involve a lot of clever ideas in the proof. But this rather humble looking result that we can actually define exponentiation was one of the very nice, clever contributions that Gödel made in his proof. And the proof is not at all obvious how to do this, and it's going to take us quite a bit of work to get that. And then once we've done that, we'll see the ideas that are behind this don't just apply to the exponentiation operation, but actually are powerful enough to show us that any function that we have an algorithm for, so any computable function, is also definable in the language of arithmetic. Right. So we're going to basically look at how to define stuff in this signature. So let's start with some abbreviations. Some convenient abbreviations. So this whole idea is kind of defining entities, mathematical entities. So I haven't said what we're defining because there wasn't space, but anyway, sort of defining mathematical operations and concepts in the language of arithmetic. So let's start off very basic. I'm not happy with any of the pens today. So firstly, something really trivial. So for any natural number n, this is a natural number in that sort of platonic world of mathematical things. We identify a constant, so not a constant, a closed term, so a term with no free variables in the language of arithmetic that represents that number. So we define, this thing is called its numeral. So its numeral, which is often written as n underline or overline. I seem to have overline in my notes, so let me stick to that. It's numeral n overline. So this is a closed term representing n. And this is just trivial, so yeah. So the numeral representing 0 is the constant symbol 0. The numeral representing 1 is the closed term successor function symbol applied to 0, and so on. Basically, the numeral representing n plus 1 is the successor of the numeral, that's a successor, not 5, of the numeral representing n. Okay, so that's really trivial. So, for example, we can state this using the sentence, Google equal the sentence, which is true, that Google equals, Google equals Google. Google is the number that kind of the search engine and company Google was actually they chose their name based on Google, although they spelled it differently, but the Gödel is 10 to the power of 100. That's a completely silly number, but anyway. So we could have the sentence Gödel equals Gödel, but if you actually wanted to write it down using this notation with these numerals, the numeral for a Gödel equals the numeral for a Gödel, you'd be hard pressed to probably fit your formula into the universe, I guess. So this is a very inefficient way of representing numbers. You can come up with much more efficient ways of representing numbers than this, but this has the benefit of simplicity. Anyway, we're not ever going to need to write down specific formulas involving large numbers. So for us, this is going to do. But I just want to make the point that actually, for any practical purposes, this is a very bad notation system for numbers. So then we're going to have some other formulas, some formulas that we can define, and classes of formulas. So hang on, I need to find the right button. So given any two terms, T1 and T2, we can write the formula T1 less than equal to T2 using definition that we've had many times. So there exists y T2 equals T1 plus y. And this is okay because the whole point is we're now considering quantifiers ranging over the natural numbers. We've seen this many times before. And T1 is strictly less than T2, would be, well, you could put and not equal to, but we could also have exists to y, T2 equals T1 plus y plus 1. Example. And then it's often going to be useful to have what are called formulas involving, rather than arbitrary quantification over all numbers, quantification over bounded, so what's called bounded quantification. So where we bound the range of a quantification. So we can bound by a non-strict inequality, or we can bound by strict inequality. So this is, we've got some formula A on the right, and we're forming a more complex formula where we've got a bounded quantification in front. And it's not that hard to see how to define this. So for all x less than equal to t, A holds for all x less than equal to t is simply saying for all x, if x is less than equal to t, then A holds. And the existential formula, there exists an x such that, and then of course it needs to be such that x is less than equal to t and A holds. And the strict bounded quantifications, you simply use the strict inequalities here instead. Just to emphasize why I'm writing it in this way, we have such a, obviously when you quantify, you need to quantify over a variable. For all x, x needs to be a variable. But the point is, as the bound, we're allowed to use any term. Yeah. Okay. And that fits in with this pattern for how we're writing the formula. We've got some, we can put any term in this position on an inequality. Okay, so we can use complex terms in here. So we can give, for example, using addition and multiplication, we can quite easily give polynomial bounds on polynomial bounds on a variable. So these defined formulas here, these are called, so this process of bounding quantifier here is simply called bounded quantification, for the obvious reason. And the reason for identifying exactly these things is that this allows us to define a class of formulas, which we can think of a class of simple formulas. Formulas in which are very constrained in how we can form them. And this is going to be useful because we're going to then show that lots of mathematical concepts are actually definable not just by arbitrary formulas, but by simple formulas. And these simple formulas will have quite good properties. But another way of motivating this is, we've got our signature, L sub A, that I just rubbed off the board. And then we've got the way of generating formulas using logic, so we can combine atomic formulas using the logical connectives and quantifiers. And if we do this, we can say very, very complicated things. So if you do discrete mathematics, where you're quantifying over, where you're talking about discrete structures, whenever you get properties that are of the form, for all this, there exists a that, such that for all this, there exists a that, which sometimes you get this kind of thing, these properties become very, very difficult to think about. And such complicated properties, you don't need to be used to do simple things. And we're going to look at now classes of formulas that avoid such arbitrary alternations of unbounded quantifiers. That wasn't really very good motivation, but there's a better motivation, which I'll be able to say in a moment. So we're going to identify two classes of simple formulas. The first ones are called delta zero formulas. So this is the smallest collection of formulas. We're always working in the language of arithmetic, but this is LA formulas, and let me just write it explicitly here. I'll just put that in brackets because I don't want to keep on saying it every time it applies. So by default, we're always talking about the language of arithmetic. So it's the smallest collection of formulas containing atomic formulas. Well, the atomic formulas, we didn't put any predicate symbols in, so they're simply equalities. We also allow it to contain the inequalities, defined in this way, the strict and non-strict inequalities. And then we close this under, so we allow combinations of such formulas under all propositional connectives. Well, all propositional connectives here, but e.g. and, or, negation, implication, that's pretty much all of them anyway. And of course, first order formulas are atomic formulas closed under propositional connectives and quantifiers. Here we start off with not just atomic formulas, but also the inequalities, and we close under propositional connectives and bounded quantifiers only. Bounded quantifiers. Okay. And the motivation for considering such delta zero formulas is, if you have a delta zero formula and you give some numbers as values to the free variables in the formula, then the property the formula states is then decidable. because the formula is simply a propositional combination, a combination of bounded quantifications, where the bounds are always upper bounds. So bounded quantifications, either universal or existential ones, and combinations of propositional connectives. And you can decide if such a thing is true, because whenever you have, for example, for all x is less than or equal to t, if you've given values to all the free variables, t has some given natural number value, we've only got finitely many cases to check. Okay, so the important property of delta zero formulas is if you fix the free variables, or an important property, if you fix the free variables, then the property it states, if you fix the values of the free variables, the property it states is then decidable. And that's one collection of formulas. And we're going to show that many useful relations between numbers are definable by delta zero formulas. But in the end, we want to show that the exponentiation function is definable. Actually, that's not going to be definable by a delta zero formula. And one can prove that because I mentioned a decidability property. Actually, from the way we define this, those who know about computational complexity, all the properties defined by delta zero formulas are decidable in polynomial time. Whereas the exponential function, the graph of the exponential function, which we're going to show has a representation, is not something that you can decide in polynomial time. So it can't be defined by a delta zero formula. I think that's correct, what I said. Anyway, what we're going to show is it's defined by the next class of formulas, and these are called the sigma 1 formulas. So sigma 1 formulas so these are formulas of the form some number of existential quantifications. So let's make n of them. So n is greater than or equal to 0 here. So some finite number of existential quantifications followed by a formula A, where A is a delta zero formula. For those who are sort of tuned into the computational aspects here, doesn't matter if you're sort of finding these remarks a little bit cryptic, so complicated to understand. But for those of you who are tuned into the computational comments here, so now if we fix the values of the free variables in this formula, so the free variables don't include the x1 to xn, we now want to see if we can decide if this formula is true. Well, we're asking, do there exist x1 values, x1, x2 up to xn, that makes this decidable property true? But there are no bounds here, so we don't know where to stop. But if we ever find such an n tuple, we'll be able to test it and see that the value is true. So this is, in general, a semi-decidable property, not a decidable property. And it turns out that sigma 1 formulas represent all and only the semi-decidable properties of natural numbers. But for the moment, it's just a class of formulas that's expressed in this way, and we're going to see that the exponentiation function is definable by a sigma 1 formula. Okay, so main result today. Exponentiation is definable or representable, we're going to say, by a sigma 1 formula. Okay, it's slightly before the break, but this is a good stopping point. And I'd like you over the break to fully understand these definitions of delta 0 and sigma 1 formulas, because that's going to be really important for what's coming up. So if you've got any questions on that, I'll just pause the recording and right, so as I said at the end of the last part, a goal is to show the main goal today is to show that the exponentiation function is definable by a sigma 1 formula. So first I'm going to say what it means for a function to be definable by a formula. But before doing a function, we do the slightly simpler case of a relation. So we say that a relation, a formula. Oh dear, that's the wrong pen. I should have prepared properly. So a formula. It's also the wrong pen. We can do one thing with each pen until we get them. So a formula A with 3 variables x1 through to xk. As we know, we view this as a defining a relation in k variables. So we can formally say, well, we're going to say this represents a relation, a k-ary relation on natural numbers. Okay, time to change again. A k-ary relation R, that's better. So a k-ary relation one can view as a subset of n to the k, or let's view it as a function that assigns to any k tuple either true or false. So we just make the obvious definition that the formula represents a relation on natural numbers. The point is we simply want to interpret the language as expressing properties of natural numbers. So we interpret the logical formula as whoops. Okay, so all this is saying is the formula represents the relation that of k tuples, this is supposed to be an n1 here, k tuples of natural numbers, that formula makes true under the interpretation of the formula in the natural numbers structure. So I'm being a little bit sloppy in my notation here. So what this red bit, to be more pedantic, so the red bit means, if you like, a really very pedantic way of doing it is in the structure curly n, which is the structure of the natural numbers, then the formula A is true under the environment that maps x1, the variables x1 through to xk to n1 through to nk, where n here is the structure that has the natural numbers as its set and the usual interpretations of plus. But anyway, I'm not really saying very much here. It's simply formula, this is simply saying how a formula in this language of arithmetic represents a k-parity relation on the natural numbers. Okay, so let's pop a box around that. But exponentiation is a function rather than a relation, so we want to know what it means for a formula to represent the function, and by that we're simply going to mean that the formula represents the graph of the function. So recall, I mean, this is all basic stuff, but I might as well go through the definition just to be complete. So recall that the graph of a k-ary function so that's the k-argument function on the natural numbers, so from n to the k to n. So the graph is the k plus 1ary relation which I'll call graph of that. So this is a k plus 1ary relation, so it maps k plus 1 tuples of natural numbers to true, false. And it's simply, the graph is defined by that the graph of the relation, the graph of the function is true for a k plus 1 tuple n1 to nk and m, if and only if in the case that m is the result of applying f to n1 to nk. So hopefully we should have all seen this concept before a long time ago in Logika, in Logika, or in some related course if you're not from Vienna. Right. So that's the graph of a function. Just remind you, because we're going to be interested not just in functions, but also in partial functions, which are functions that are not quite everywhere defined. They're defined on a subset. So recall that a relation R, a k plus 1ary relation R, is the graph of a function if and only if it satisfies two properties, which I'll call 1 and 2. So one says that if you ever have a k plus 1 tuple n1 through to nk and m, and another n1 through to nk with the same n1 to nk and a potentially different m prime. So these two both hold if and only if n equals m prime. So this is saying for any k tuple, the relation assigns at most one number m to that k tuple. And secondly, that it's a function, the graph of the function, if for any k tuple, it does assign at least one value m to the relation. So for all n1 through to nk, there exists an m such that n1 through to nk and m is in the relation. So this is called, this first property here is called single valuedness. Single valued. And this is called total. And R is the graph of a partial function and only if it satisfies what? Just what? So I wanted to mention this because partial functions are going to play a role later, and the partial function is like a function. It's single valued, but it need not be defined on all k tuples of numbers. Right, so we say, the last bit of the definition of representing, we simply say a formula A represents a partial function. It's a formula A x1 through to xk, and let me see if I give the variable a special name. Let's call it z. So this is a k plus a formula where it has at most k plus 1 free variables, x1 through to xk, and z represents the partial function from n to the k to n. So I use this partial arrow to say that something might be, say that a function might be partial. So if it represents the graph of the function. So the point here is we've defined what it means for a formula to represent a relation, and to represent a function, we use to represent a k-array function or partial function, we use the notion of representing a relation, and we require that it represents, we have a formula with k plus 1 variables, we require that it represents the graph of the function. All right, and so what we're going to show, now state finally the theorem we're going to prove at the end. A lot of machinery so far, it's all very basic stuff, but it's a bit, requires some fussy definitions, but so theorem, which is going to take a bit of work, the exponentiation function that maps natural numbers x and y to x to the power of y. But this is a function from n squared to n. One slight issue with, if we wanted it as a total function, is we need to give a value to 0 to the power of 0. So I will give a value to 0 to the power, I mean, we could have it as a partial function if we wanted, but I am going to give it a value to 0 to the power of 0. We're going to take the value 1 as 0 to the power of 0. So the exponentiation function is definable by a sigma 1 formula. Let's say gx, which is going to have 3 variables because, so it's representable, I mean, one could say definable as well, it wouldn't be wrong, but it's representable by a sigma 1 formula. 3 variables, so the last, we're representing the graph of the function. Right, so that's what we want to prove. Right, good. So we can actually get down to business now. Having the machinery in place. And essentially what we're going to do is we're going to first prove a few simple things are definable. And the simple things are actually all going to be delta 0 definable. So formulas that just involve bounded quantification. And then that's not going to be very difficult. And then we're going to have the main result that allows us to combine those simple things something much more complicated. And that will enable us to prove the theorem. Right. Oh, we're only going to do two simple things, actually, so good. They're not going to take very long. So the first one is going to be a partial function is representable. So the partial function in two arguments that takes an x and y and maps it to x. So what might write x mod y, or computer scientists would, people who are in programming languages would often write x% y. That's a standard notation. So what this is, the remainder when you divide x by y. So while I'm writing that down, why is this a partial function? Difficult question. Why is it a partial function? And in what case is it going to be difficult making sense of this? Come on, this was 0. Yeah, in the case that y is 0, it's going to be, it's hard to give a sensible answer to what this should be. You certainly don't want to divide by 0. This partial function I haven't finished is delta 0 representable. So we want to represent it by a formula with three free variables, x, y, and z. And we basically want to say property that the property holds for x, y, z if z is the remainder of when you divide x by y. So proof. We use formula. And actually, we can basically state this very directly. So we want to say z is the remainder when we divide x by y. So we want z to be strictly less than y. And there exists a w such that x equals y times w plus z. So this was a correct formula. We're saying we can get x as a multiple of y. Sorry, we get x as a multiple of y by adding z, and that must be the remainder because z is forced to be less than y. This is a correct formula stating the property. It's not yet correct for showing our lemma. Why is that?
Because there's an existential quantifier that's not bounded.
Indeed, we've got an existential quantifier that's not bounded, but how can we bound w?
It's just supposed to go up to x.
So indeed, so x is going to be the product of y times w, so w can certainly, because we've only got natural numbers, we can certainly bound w here by x. Okay, very good. Right, good. So that's the proof of that. So that's very simple. So the next lemma is another function that's let me see if I can focus the camera a bit better. So we're going to make use of a pairing function on the natural numbers, and this is the one I always like to use, and it's very easily defined here. So the function, which I call p of xy. So this is a function, again, a binary function on natural numbers. This time it's total. In fact, the important property of this function is that this is a bijection. It's a bijective function from the pairs of natural numbers to natural numbers, defined by the definition I like is p of xy is a half of x plus y times x plus y plus 1 plus x. And again, this is delta zero representable. And just to show you how this pairing function works, take a few seconds. We've got x here and y, so we've got 0, 1, 2, 3, 4. 0, 1, 2, 2, 3, 4. So the x is there. So here's x and here's y. So this function goes like this. Counts along the diagonals. So we have 0 here, and then we get 1, 2 along the next diagonal, going from northwest to southeast, and then 3, 4, 5, and then 6, 7, 8. Hang on. I seem to be getting the rows a bit mixed up. 6, 7, 8, 9, 10, 11. Anyway, so on. So it's an easy way of pairing up natural numbers, and it's particularly useful for us because it's defined using just multiplication and addition, so it's easily defined in our logical language, except we have to make sense of this 1/2 times, which here it's okay because we can see that one of these numbers is always going to be even, so we can always divide that by 1/2. Anyway, how are we going to do that in the logic? Well, so again, we want now a formula pair of x, y, z, and this is going to be, we want a bounded quantification. So we want 1/2 times x plus y times x plus y plus 1. So the way of that is saying there exists a w, which is going to be the 1/2 times, such that w plus w, so twice w, is x plus y times x plus y plus, well, let's be very pedantic, s of 0, and z is w plus x, okay? So w is this part here, and we do that 1/2 by this. So once again, I've put an unbounded quantifier here. This is a correct formula that represents the pairing function, but it's not yet a delta zero formula. So again, we need to find a bound for w. So what would a good bound for w be here? Any suggestions?
Z.
Yeah, so we can perfectly well bound it by z because, you know, w is definitely going to be less than or equal to z. So this is w less than or equal to z. Okay. Right. So we've shown two easy functions are delta zero definable and delta zero representable. I mean, as I keep on saying, definable is not a wrong word, but I'm going to use representable. So having done that, we now get to the main lemma that's going to make things work. So we've just done a function that encodes pairs of numbers. The crucial thing one needs to do to define functions like exponentiation, to represent those using a logical formula, is to have a way of coding arbitrary length finite sequences of numbers as a single number. Now that's not a particularly hard thing to do. There are all sorts of, it's not particularly hard to find nice, simply defined functions that encode finite sequences of natural numbers. One way to do it is using prime factorization of natural numbers. So you might have, you use a natural number to represent a sequence where the first number in the sequence is the number of zeros that appear in the prime factor, is the power of 2 that appears in the prime factorization, and the next number is the power of 3 that appears in the prime factorization, and the third number is the power of 5 that appears in the prime factorization. You have to actually slightly adjust that to make it encode finite sequences in. Anyway. Yeah, you need to know how long this. Anyway, you can do it that way. Another natural way uses powers of 2 and some binary essentially binary representation of sequences of natural numbers. The problem with all these sort of easy methods that naturally come to mind is they all make use of exponentiation in the way that you define them. So we need to be able to encode sequences in order, as it's going to turn out, in order to show that we can represent exponentiation. We don't have exponentiation available until we've done this. So we need to find a way of encoding finite sequences of natural numbers without using exponentiation. And to do that, we're going to prove a lemma that says we can do it, and then one clever thing is identifying exactly this right lemma, but the main clever thing is then how you prove this lemma. And this lemma is called Gödel's beta lemma. So this was, as I say, one of the clever contributions that Gödel made in steps towards this proof. So Gödel's beta lemma. We're going to have a function that codes finite sequences in a certain way. And I'm just going to say what the function needs to do without actually defining what the function is. Then later on, we'll define such a function. That's going to be the tricky bit. But we're going to call the function beta. So there exists a mysterious delta zero representable. So it's still delta zero representable, so still by simple formulas involving only bounded quantification. Binary function beta n squared 10. So binary function for natural numbers to here, satisfying that for every k greater and for any sequence of natural numbers of that length, there exists a natural number s, which we think of the coding as a natural number of this finite sequence n1 through to n. Lemma is encoding as the representation of the finite sequence n1 through to nk, such that, and the point is, all we need to be able to do is extract the elements of the sequence, the n1 through to nk from S. That's the important thing we need to be able to do. So such that beta, if we apply the function beta to the encoding of the sequence and to a number I, between 0 and, oh, sorry, this is it's a k length sequence, but I'm going to actually index it from 0 to k minus 1, just so that we can use numbers from I strictly less than k as the indices. So if we apply the sequence, if we apply the beta function to the encoding S of the sequence, the number encoding the sequence, and its index, and the index of an element, we get back indeed the element n at the index, so the relevant element of the sequence. So this should hold for all I strictly less than k. And a further property that's going to be useful in order to use S then later as bounds in quantifiers, we're going to note is that a further property of the way we encode this is that S is greater than or equal to the max of all the elements occurring in the sequence, n0 through to nk minus 1. Okay. So when you encode a sequence of numbers, your encoding of the whole sequence is not miraculously smaller than the number itself. We don't want that. Okay, so we think of S as a single number encoding the k tuple. So let me write that down. It's quite useful to have this in the notes. And think of, I've already said it, but think of S as a single number encoding the sequence n0 up to nk minus 1, n0, n1, nk minus 1. And beta extracts entries in the sequence. Right. So two things we're going to do. One is to prove this beta lemma with this, which means giving a mysterious function. And the other one is to prove the theorem, which is that exponentiation is sigma 1 definable. And we can prove that directly from the lemma. So the way I'm going to do it is I'm going to do the latter one first. I'm going to prove the theorem that if we have the beta lemma, that exponentiation function is definable. And then the last part of the lecture is going to be the clever proof that this beta function actually exists. How one uses the beta function to define exponentiation is a little bit clever, but nothing sort of really shocking. It's not the main difficulty. This is good. So it's good to get that out of the way. Okay, so what we want to show is the proof that function xy maps to x to the power of y. The exponentiation function is delta is sigma 1 representable given the beta lemma. So what we need to do, we need to define a sigma 1 formula. Let's say x, y, z, such that x holds of x, y, z, if and only if z equals x to the power of y. And we're going to use the beta lemma. So the beta lemma tells us this beta function with this nice properties that it allows us to extract the element of the numerical encoding of a sequence of natural numbers. We're going to use the fact that this is delta 0 representable. So let G beta, sorry. It's getting into topology there. A mistake. G beta of S, I, Z that this be the delta 0 formula representing the beta function. So in other words, this represents the beta S I equals Z. So I'm using now S and I as variables to somehow just be suggestive of the statement of the beta lemma. So the first variable here is the encoding of a sequence. The second variable we interpret as the index, and the property holds of S, I, and Z if indeed Z is the entry at index I in the sequence encoded by F. Right. So I'm just simply going to write this formula down. It needs to be a sigma 1 formula, so it needs to begin with an existential quantifier and unbounded, so we're not going to be able to use a bound on the existential quantifier. So x of x, y, z simply defined to be equal to, and let me fill up the board with it. So there exists a u such that I'm going to use S. So I always I'm always reluctant to depart from the notation in my notes because it always comes back to bite one later when it happens. But I don't see any reason not to use S here, and it looks more intuitive. So there exists a number which is going to be encoding sequence such that when we use the delta 0 formula for extracting the element of the sequence, and we extract the 0 index element from the sequence, we have 1. And for all numbers I less than y, so y is going to be the length of the sequence here, and here we're ranging over the indices of the elements of the sequence. There exists an R less than equal to S, such that G beta of S I R and G beta of S R, right. I'm going to put I plus 1 here, but of course I mean successor of I. but I don't want to put S in now because I don't want to confuse with this S. So this is probably the reason I used U when I wrote my notes. Anyway, so, and here we have R times X and G beta of S Y Z. Okay, so what's this saying? Is view it as this. There exists a number encoding the sequence S, encoding a sequence S, which we're going to have length Y. So intuitively, S encodes, let's say, N0, 1 to N Y minus 1. So it's some sequence of numbers of length Y. That's what we're thinking of, although, I mean, there's nothing saying it's a sequence of length Y, but this part here is saying it can actually be a longer sequence, but we're only going to look at the first Y entries of it. And the first part says that N0 is 1, so such that N0 is 1. And the second part says that for any I less than, it's actually going to be of length Y plus 1 here. So we're going to have indexes going all the way up to Y. It's going to be of length Y plus 1. And the second part says that for all I less than Y, so for all indices of entries apart from the last one, if R is the entry at index I, we have R times X at index I plus 1. So we have that N I plus 1 equals X times N of I. So we look at, so N1 is going to be X, because it's X times 1. N2 is going to be X squared. N3 is going to be X cubed. N4 is going to be X to the 4th. So Ni, so i.e. Ni plus 1 equals X to the I plus 1. It follows, well, that follows from, let's put that, it follows from this. And these imply for all I less than equal, for all J less than equal to I, to Y, Ni equals X to the power of 5. And lastly, we say that Z is X sub Y. X sub Y. And so we've forced the Y entry of the sequence to be X to the power of Y, and when we take the Y index element out, we want that to be the result Z of our property.
Is that X sub Y or N sub Y?
Yeah, sorry, N sub. Yeah, thank you very much. It's X to the power of Y, but it's actually N sub Y. Very good. Right, and the last remark to make about this is we've used an unbounded quantification here. So could we find a bound for this? Well, in a sense, we don't know because we don't actually know how the beta lemma works. So the point is we're going to need to find some encoding of this sequence x0, x, so this sequence 1, x squared, x cubed, x to the 4th. We're going to need some encoding of such a sequence here. So can we give an upper bound to where we need to look for that? Well, you can imagine the encoding is going to be complicated, but you can sort of see to encode such long sequences, you're going to need something at least exponentially big to get there. So we actually don't have any tools to give a bound here until we've got exponentiation. Once we've got exponentiation, we would be able to sort of use, if we were allowed to use exponentiation in bounds, we might be able to give ourselves some bound, although we don't actually yet know how this beta function is working. But certainly given what we know, we can't put the bound here. And given that in our language, our bounds need to be essentially polynomials in variables, we're not going to be able to ever give a bound here. So this is a formula that really is a necessarily delta, sorry, not delta zero, but sigma one formula. We can't use bounded quantification here. One thing to say here is that the existential quantifier we had in the middle here, that appears inside a bounded universal quantifier, this needs to be bounded here because it's in the middle. We were able to bound this by the sequence S because of this parenthesized remark at the bottom of the beta lemma, which tells us that S bounds all the values in the sequence. So this, sorry, I've never closed the bracket here. So this bound here is justified by this part of the beta lemma. Okay, right, well, okay, it's 58 this time, so this time we're going to start at 13 minutes past 10. Right, so the remaining thing to do is prove Gödel's beta lemma. The easy thing is actually to give the delta zero formula that represents beta and to define what beta it is, to define what the function beta is, and to give the delta zero formula that represents it. The interesting part is why it works. So let's define beta first, and then the proof of the beta lemma. But this I certainly need my notes for, because I can never remember the exact detail of the formula. So the beta function is the function, so it's a two-argument function. We'll call its arguments S and I, like in the lemma. And we need to interpret S as an encoding of a sequence and I as the index. And to do that, it turns out to encode, it's useful to encode sequences as pairs. So S is going to be represented, it's going to be a number, but we're going to interpret it as P of two numbers. So our pairing function P applied to two numbers, A and M. So we're going to interpret S as PAM, and then the value we return is A modulo, so we're going to use our modulo function that I defined before, A modulo I plus 1 times M, that's I plus 1 times M plus all plus 1. So where AM are the unique numbers such that S is the pair obtained by the pairing function that we had before, the one encoding square of natural numbers as a single natural number. So S is obtained from the pair PAM. So we need to extract encoding of S as a pair and then do this modulo arithmetic thing. And the reason it's going to work is because of the Chinese remainder theorem. The Chinese remainder theorem tells us that using modulo arithmetic, we can combinatorially encode sequences as remainders, basically. But obviously, it's a little bit fiddly because there's all this sort of bit of a formula I plus 1 times M plus 1. Anyway, given this particular function, so that's the definition of the function, we can show that it's easy to show that's delta zero represented and representable. So this is represented
by the delta zero formula. I was calling it G beta before. So G beta of S I Z. This is going to be true if Z is S and I as above. So we need to say that there exists an A and there exists an M such that S is the pair of AM according to the P function. So we had a delta zero pair relation for that. So S is that. And then Z is the remainder of A divided by I plus 1 times M plus 1. Once again, this is going to be delta zero, so we need to put bounds on the A and the M. But by our pairing function, it's clear from the pairing function that whenever you pair an A and M together, the value of the paired function is always greater than or equal to the pair values themselves. So we can simply bound both of these by S. Okay. And the other thing is, why does this function beta satisfy this property here, that the encoding of a sequence is always greater than or equal to any values of the sequence? Well, we're getting the values of the sequence out by taking so S is a pair of something, and we're taking some number A modulo some other number, and it's clear that the value of the sequence is always less than or equal to this number we're moduloing by, and since oh no, hang on. The value of the sequence is clearly less than A, less than or equal to A, and S is greater than or equal to A, because the pairing function increases values. Right, okay, so the question is, why does this work? I've already mentioned it's due to the Chinese remainder theorem. That is, the Chinese remainder theorem essentially enables us to do it, but there's still some details to check once we've got the Chinese remainder theorem. So I'm going to remind you what the Chinese remainder theorem says. So we'll state that, and then we'll apply it to prove this result. I mean, Chinese remainder theorem is classic mathematics going back to ancient China. And just out of interest, how many of you could actually give a statement of the Chinese remainder theorem just off the top of your heads? How many of you have seen it before? I mean, probably everyone's. Yeah, right. That's not everybody, but anyway, most people have seen it. It's not a difficult result, but it's a classic, as I say, a classic result of maths. But could anyone state it? I'm not going to test you. I'm just interested. Yeah, it's the kind of thing. Sort of, if you know the idea of it, then with enough time, you should be able to. You should be able to find the statement yourself. Anyway, let's. So the Chinese remainder theorem is a lovely result in basic number theory. CRT for short. So if we have k natural numbers, let's call them m0 up to k minus 1, mk minus 1. And they need to be pairwise co-prime. That is, So if our pairwise co-prime, so this means i.e. there is no prime number that divides two distinct mi and j. Or in other words, if we express each of these as a product of primes, we'll have different prime numbers occurring in every case. Product of powers of primes, if you like. So if they're pairwise co-prime, we've got pairwise co-prime numbers, then for any n0 less than m0 up to nk minus 1 less than mk minus 1. So for any, so we've got a sequence of k pairwise co-prime numbers, and for any sequence of strictly smaller numbers, there exists a unique number A strictly less than the product m0, m1, product of all the m's, such that A modulo mi equals ni for every I less than k. Okay. Box around. Well, I won't put a box. I'm putting box around important results for this course. This is not an. I mean, it's important because we're going to use it, but it's not the content of this course. So what it essentially says is, if you've got k co-prime pairwise co-prime numbers, then you consider the product of them, and the numbers up to those k, up to that product, all the numbers below that, all those a's, that's in bijection. That can be put in bijection with the set of sequences of k numbers, each one less than the corresponding, so each ni less than the corresponding mi. So modulo arithmetic gives a bijection between the product of these, the product of the sets of numbers 0 up to m0, 0 up to m1, 0 up to m2, where it's strictly less than. Let me write it. So this gives a bijection between the product of 0, the interval of natural numbers 0 up to, well, actually, let me write it like this. So m0 times m1 times k minus 1 to m0, m1, m2, mk minus 1, where by square brackets m, I mean the set of natural numbers from 0 up to m minus 1. So, okay. So modulo arithmetic establishes a bijection. That's a way of thinking about it. Between sequences of this form, k tuples of this form, and numbers up to the bound here. Okay, so given the Chinese remainder theorem, we want to prove that the beta lemma works. So we need to show that that the beta function does its job. Well, there exists. We need to show that there exists a number s such that the beta lemma, the beta function, does its job. So now continuing the proof of the beta lemma.
And let's try and squeeze it onto the board here. Well, actually, we'll just see how it goes. So continuing proof of the beta lemma. So we're given k greater than or equal to 0, and we're given an n tuple of numbers, and we need to find the number s that's going to represent that sequence n0 to nk minus 1, such that the beta function is going to do its job. We're given k greater than or equal to 0 and n0 n1 up to nk minus 1. And the Chinese remainder theorem is encoding sequences, but we can't use it directly because we need to find, in order to encode the sequence, we need to find a suitable k tuple of pairwise coprime numbers. So that's basically where we need to do a little bit of work, but it's not very hard. But in order to get enough pairwise coprime numbers, we need to use some rather large numbers. So we let m be the maximum of k and n0 all the way up to nk minus 1. But we factorial that. Okay, so we're dealing with rather huge numbers here. So just to emphasize, that's not an exclamation mark, that's factorial. And now we're going to define our bounding numbers m0 to mk minus 1 that are all pairwise coprime. So for I from 0 to k minus 1, we define mi to be, right, this looks a bit fiddly, so right, it's I plus 1 times m plus 1. So notice this is appearing in this formula here. Okay. And the claim is that, so we've got an m0 up to an mk minus 1. The claim is we want to apply the Chinese remainder theorem. The claim is that these are all pairwise coprime. So we claim m0 up to mk minus 1 are, these numbers are pairwise coprime. Right. So suppose not. So if they're not pairwise coprime, we have two distinct ones of these. So we say mi and mj with some common prime divisor. So then p divides mi and p divides mj, or some prime p and distinct ij. So p divides mi and mj, then p divides mj minus mi. In fact, rather than distinct I and j, we can, without loss of generality, assume that I is the smaller one. So we've got I strictly less than j. So p divides mj minus, it divides both mj and mi, it divides both, it also divides mj minus mi. This is like Euclid's algorithm for the greatest common divisor. This observation is part of that. So the way we've defined mi and mj, if we subtract mi from mj, we get j minus I times m. So P divides j minus I times m, just from this formula that defines mi and mj. But also, j minus I divides m, because j is less than or equal to k, and k is less than or equal to the number we were factorialing, so all numbers up to the maximum of this divide k. So since j minus I is less than k, also j minus I divides m. But P divides j minus I times m and j minus I divides m. That means that P divides m. Yeah. Prime will need to divide one of these, and if it divides j minus I, or since j minus I also divides m, P also divides m. So P divides m, hence if P divides m, it divides I plus 1 times m. But we started that P divides mi, which is I plus 1 times m plus 1. But P divides mi, but i.e. P divides I plus 1 times m plus 1. And that's a contradiction. You can't, the same prime number can't divide one number and its successor. So that's a contradiction. That's it. Okay, so these numbers are pairwise coprime. Right, so the question is, which bit of the board don't we need anymore? It's a good question. Maybe we don't need the Chinese remainder theorem, even though we're about to apply the Chinese remainder theorem. But the Chinese remainder theorem, you all have. We can remember the Chinese remainder theorem. So we'll go back here. That's part of our general knowledge about mathematics, whereas everything else was new to this lecture. So we've rubbed it off, but the point is we're now exactly at the point that we're going to apply it. You might think I'm doing some trickery here because I'm rubbing off what I'm applying and then I'm saying I'm applying it and you can't actually check it. But honestly, this is, I'm being honest, and if somebody says to you, honestly, I'm being honest, you should be suspicious, but not in this case. So where are we? Yeah, we've got these are pairwise coprime, so we can apply the Chinese remainder theorem. So the claim holds. Let's write that down. We made the claim holds that they're all coprime. So apply Chinese remainder theorem. So this gives A coding the sequence So all these mi's are clearly greater than all the ni's because we were making a huge number much bigger than the ni's. So this gives so So our mi's, one of the sequences it encodes is the sequence of the ni's. So this gives us an A, the Chinese remainder theorem gives us an A such that mi mod, sorry, A mod mi equals ni for all I mod k. But this is saying, so that's saying that's A mod I plus 1 times m plus 1 equals ni whole 1. So this should be from 1 to k minus 1. So this I from 1 to k should be from 0 to k minus 1. So all we need to do is S equals P AM and beta of SI equals NI for all I from 0 k minus 1. Because that's exactly how we've defined the beta function here. So this is as required. Okay, so that is the proof of the beta lemma. And we've basically done the job that we wanted to do, which is proving that the exponential function is representable. And although the proof is somewhat complicated, the formula itself is not actually that complicated, because the formula itself was that formula that I called x at the relevant point, and the formula I called x included within it as subformulas the formula g beta, but the formula g beta is also, I mean, it contains the pair and the remainder, but those were not very, very complicated formulas. So in the end, if you take the whole function, the whole formula that you've got representing the exponentiation function, it will fit, you know, I could easily fit it on one of the panels on the board, for example, if I wanted to write it down, but I don't. So we're nearly finished. I just want to mention some sort of where one goes from here. Maybe we'll go to the other board. And we showed that the exponentiation function is delta is well, there's a mistake in the notes, is sigma 1 representable. Exponentiation is sigma 1 representable. Essentially relied on the following. On the exponentiation is defined by what people call primitive recursion. That is, we made the observation that to define exponentiation, we define it by a base case, x to the power of 0, and that's defined to be 1. And I should have mentioned at the time when we put that bit in the formula, this is at the point at which we're assuming that 0 to the 0 is 1 in order to have this uniform definition.
And then x to the power of n plus 1 is defined recursively. We define the exponential function recursively by multiplying the recursive call to x to the n by x. So it's a recursive definition that one could program in this way, but it's a particular form of, very simple form of recursion called primitive recursion, where everything is just done, you define the successor case in terms of the previous case. You don't do anything more complicated than that with primitive recursion. So we use the fact that we can define by primitive recursion, and once we can define by primitive recursion, it's easy to specify how to define x to the power of y as using a sequence where every element of the sequence is the chain of recursive approximations to x to the power of y. So you start with the base case and you go up with the 1 case, the 2 case, the 3 case, and so on. It's almost what people call dynamic programming. You have a sort of table of all approximations there. The point is, this is not at all this whole idea is not restricted to the exponentiation function. So indeed, the same idea generalizes to all functions that can be defined using this method of primitive recursion. So they're all what are called primitive recursive functions. And these are something that people who did computability theory last semester will know very well. It was a major part of the computability course. They're going to play a sort of side role in this course, in that we've got exponentiation, but the primitive recursive functions are going to be the handle that we have in this course on sort of proper computability theory. It's going to be an important class of functions on the natural numbers that are defined using basically this kind of recursive rule, a general, formulated according to a general pattern for how one should apply this kind of recursive rule. Because it sort of plays an important but side role, I'm not going to define the primitive recursive functions in the lectures, but they're going to be the subject of this week's exercise class tomorrow. So for those of you who did computability theory and have already done an exercise class on the primitive recursive functions, it's up to you if you want to do another exercise class on the primitive recursive functions or not. There will be a slightly different perspective tomorrow in the second half, in that it's going to also involve defining primitive recursive functions using logical formulas. So that's something we didn't have on the computability theory course. But just to say, so tomorrow's exercise class is going to be about this generalization of this kind of way of defining functions that shows how we can define exponentiation from multiplication, for example. A very powerful way of defining functions on the natural numbers, and you're going to consider these primitive recursive functions systematically in tomorrow's exercise class. So I've taught them on the computability theory course, and having taught them once, I didn't want to do it twice, which is why they're being put into the exercise class this time. And given that I'm not teaching them now, that means that we're finishing early. I hope nobody complains too much. So I'm going to stop the recording